Yeah, so for number two, parts A and B, I would say zero in each case. So for part C, I would say y equals zero is your horizontal asymptote. So if that makes sense for that one. For number three, if you're approaching, well, first of all, let's rewrite it for number three. It's like saying 1 over x e to the x. Hope that makes sense for that one. So if x is approaching positive infinity, what do you think is going to happen? What's the limit going to be? Is x approaching positive infinity for that one? Yeah, because the bottom just keeps getting bigger. Now for part B, this is a little bit interesting. If it's approaching negative infinity, so actually, let me write it back to how it was originally, right? By playing a negative infinity, you're really doing this, right? What do you think is approaching when that's happening? Good. And why is that?
Because e to the power that is going to be bigger than negative.
Yeah, it's more dominant. Exponential functions are more dominant than monomials or power terms or linear terms. So, and if your graph, you see it for yourself, but because the bottom does get negative still, like say you plug in 1,000, sorry, negative 1,000, you have e to the 1,000, which is crazy big over negative 1,000. Again, we're playing negative 1,000, but it's e to negative x originally. So overall, that is going towards negative infinity. Now, there's still a horizontal asymptote, of course. It's at y equals zero. So that's how that would look. And for number six, this one has two, I think, right? You should have two. For number six, if I let x, now if I rewrite it, it's kind of like saying 2x minus 1 over x minus 3. Or you could write as 2x minus 1 negative x minus 3. This would be true when x is larger than 0. This would be true when x is less than 0. You guys would agree? I didn't realize the piecewise was going to be a little lazy, but if an x approaching positive infinity, what's the ratio of those leading coefficients? So it's 2. But if approaching negative infinity, it should be -2. So you have two horizontal asymptotes, y equals 2 and y equals -2. Okay. So hopefully it makes sense for that one. Okay. And then, so I signed those two, sorry, those three for sure. Then I also signed, yeah, page 10, numbers 1, 2, 3, 4. So let's do that. And then that should be the homework. Hopefully the homework was manageable. Okay. So page 10. Number one, hold on, let me double check. Yeah, number one, CD, two CD, three DE, four AB. Okay. Yeah, infinite limits, got it. Yeah, this should be pretty easy. That's just gonna be two for both those cases. This should be positive infinity for this one and negative infinity for that one. And if you want, you could always do this. 1 over x, 1 over x. So you get x plus 1 minus 6 over x. And you get 1 minus 6 over x. If x approaching positive or negative infinity, the 6 over x just goes away. So we're really just stuck with x plus 1. We can call that our end behavior model. And if you think about x plus 1, that is definitely going up forever to the right and down forever to the left. Hopefully C and D makes sense for that one. For D and E, those should both be 0. Again, you could do 1 over x squared if you did it analytically. 1 over x squared, 1 over x squared. Hopefully it makes sense for that one because you should get 0 up top. Even if you get something down below, but still 0 overall. And then lastly, for 4C, there's a 4AB, yeah. You should have 2 again. I believe you should get 3 and -3. And analytically, what you would do is you write a piecewise function. I won't get lazy this time. Okay, I kind of got lazy with the braces. Yeah, but I signed it because I made an adjustment on Schoology. Yeah, because you can't do all the problems. Yeah. So I had to pick some other problems to do. It's okay, you can do it later. It's not a big deal. But yeah, Schoology is kind of like the really what is a last line of the or the The buck stops with school, just put it that way. So we go with that. X is greater than 0. X is less than 0. Obviously, you can put an equal sign next to one of them. So you should get 3 and -3. No, because that's why I have X. Now so I have X plus 2. Yeah. Yeah, Laura, go ahead.
Um, do you like solve it first and then you kind of just like disregard the smaller numbers
Mhm.
last?
Right.
Or can you swap that order? Like, can you start off with 3x over absolute value of x and do piecewise from there?
You should. That's fine. Because the plus and plus one is negligible anyway, so it won't matter. So it's up to you. Okay. I think we're good for the homework. So anything else in the homework? Yeah, because I didn't assign much else. Okay. So let's go to the notes. Here we go. So our plan for today is to talk about infinite limits. So vertical asymptotes. I am going to skip around a little bit. So I do want to talk about extended functions. And I do want to talk about what makes things continuous. Wednesday, I'm going to talk about some miscellaneous things. I'm going to talk about the squeeze theorem and intermediate value theorem. Those are two new things. I'm also going to show you guys hard limits on Wednesday. Thursday, we're going to review for a test. I should have more clarity about the test by Wednesday anyway, but I have a lesson to do for you guys Wednesday. But I'm not going to do any material Thursday. Thursday will be a review day. And our tests will be on Monday. So a test Monday. And if you guys want, I could try to be available on Zoom Sunday night. So at least formal this weekend. Sorry. Sorry. But could have done it the weekend after Super Bowl. I didn't want to do that. Anyway, I don't care about the matchup anymore. No one does. Yeah. Yeah, maybe. Okay. Okay. Infinite limits. Here we go. So we're going to look at what happens to y when x approaches c, but when x approaches c, it does not exist. So left and right hand limits are different. Or I'm going to, when I do the left and right hand limits, they're going to be approaching infinity. So let's revisit 1 over x, which I know looks like this. Where's formal, by the way? Is it here? Oh, nice. Awesome. Okay. Um, and we have asymptotes, as you guys know. Now, here's what we're doing. Instead of looking at x approaching positive or negative infinity, which led us to have horizontal asymptotes, we're looking at x approaching 0 from the left and 0 from the right. So we're going to do the left-hand limit and the right-hand limit for x approaching 0. And it's pretty obvious from the graph, if you think about it. Obviously, it's negative infinity for this one and positive infinity for that one. When this happens, when the output, let me put this little text box here. When x approaches, x approaches a finite value, and if the one-sided limit is positive or negative infinity, then we have a vertical asymptote or infinite discontinuity. And that's what we're going to talk about on the next page when we put it all together. When x approaches a finite value, and the one side limit, and it doesn't have to be both, by the way. It could just be either one side limit's totally fine. If your output's positive or negative infinity, that gives rise to vertical asymptote or infinite discontinuity. So the equation of vertical asymptote, of course, is x equals 0 here. And what can we say about the limits x approaches 0? Well, it does not exist. And that's because the LHL does not equal to RHL. But that's a real reason for vertical asymptote. It's not, oh, it made the bottom 0. True, it does make the bottom 0. but really it's an infinite discontinuity. You guys didn't really have that discussion in Mr. Band's class last year because you guys weren't ready for that. Now you guys are, because now we're doing calculus, right? That is a calculus way of looking at it. The calculus way is a proper way of expressing this. That, oh, this one-sided limit going to some finite value of zero, it's infinity or negative infinity. It's going up or down forever. That gives rise to vertical asymptote or infinite discontinuity. And rational functions have that often, right? Um, so all you don't need all this to happen, by the way. Just need to happen at least once. As long as it happens at least once, and it could be, going up or down, doesn't really matter. That will be vertical asymptote. So let's take a look at 13. Oh, by the way, another thing I'll do for you guys on Wednesday, I'll give you guys access to my old AP Calculus AV exams that was on this unit on chapter 2. So you'll have an idea of the types of questions I'll ask, and then you could get a head start if you want to start preparing because, again, no formals this weekend. But of course, you'll have more time to do some practice. Okay, example 13. So analytically determine the following. Great, let's do it. Here's how we're going to do it analytically. I'm going to factor this first. I'm going to strongly recommend you do a sign chart. The sign chart will be applicable to all 4 parts. Now, you guys remember how to do a sign chart? How do I do it? Yeah, basically whatever makes the top 0 and bottom 0. Correct. And remember, if you think about it, always start at the rightmost interval, like plugging 4. If you plug in 4, what does the whole thing become? Positive or negative? And each factor occurs an odd number of times or just once. So what can you expect the rest of the signs to look like? All 10, good. Now we're going to add a little slight wrinkle to this. Y is 0 here, but Y is undefined here and here. So that's a 0, not an O, by the way. So this is what we expect for Y. Y is undefined at -3. Y is 0 at 2, and Y is undefined at 3. So undefined will give rise to these, asymptotes. So if I'm to the right, sorry, I'll start with -3. If I'm to the left of -3, and I see that, without doing a graph, if I'm approaching -3 from the left side, we know it's negative, right? And as I get closer and closer to -3, what do you think is gonna happen? It's gonna go down towards negative infinity, correct? You could plug in for yourself. If you plug in like -3.01, let's do -3.01. -3.01 minus 2 over -3.01 minus 3 and -3.01 plus 3. What do you wind up getting? -5.01 over -6.01 times -0.01. Well, wouldn't it be -5.01 over, it's positive on the bottom for sure, like 0.0601, I think, because you have to move the decimal point 2 places to the left. If you think about it, that's about like negative, I don't know, like -80 or 90, I don't know, something like that. But it's negative for sure, and it's large negative. So you can always do that if you're ever like kind of unsure. But the sign chart helps. That's the analytical part because you're analytically breaking down this rational function into things that, cause these shifts in sign for y, whether it's positive or negative. And if you're negative for y, you're below the x-axis. And you're getting closer and closer and closer to -3, you're going towards positive negative infinity. But it's going to be negative infinity because it's negative before you get to -3. Now, what happens if I approach -3 from the right side? Positive infinity, exactly, because of the sign chart. It's the sign chart and the fact it makes the bottom 0. It's both. And again, you could plug in like -2.999 if you want. But here, what's going to happen if I do that? If I do -2.999, don't I get -4.999? and I get negative 5.999. But what's that become? Positive 0.01. So you have two negatives and a positive, so it's going to be positive. I'm going to get rid of this. It's getting a little busy now. So hopefully that makes sense, how I'm able to think that through and think about approach. And lastly, if I'm approaching 3 from the left side, what's going to happen here? And then pause infinity. There we go. So that's how you can accomplish this without doing any graphing whatsoever. By the way, this helps you to do the graph really well. We have the sign chart. So what are my asymptotes? X equals -3 and X equals 3. I already put in factor form for you guys, so we're good there. We don't have to write that again. We're good? Let's save this for Wednesday. I don't want to do it today. It's too painful doing it on Monday. Crowds too much thinking. Okay. Let's move on to page 25. Let's talk about extended function. I think there were some things in the homework, the last homework May 6. So if it was there, yeah, I think it was this. Not mistaken. If you're confused, don't worry about it. We can talk about, yeah, I think problems like 15 through 18. Were you guys kind of stuck on that? No one asked about it. To 18 on page 6. No? Okay. All it just means is you're making the function continuous. You're forcing the issue of continuity. Before we get too carried away, we could graph this in the calculator, but if you just think about it, you can actually factor this. I know it's kind of weird. We usually don't do this, but you can. X minus 1 could be thought as the difference of squares. What if I were to FOIL that up top? Do I get back to X minus 1? Yeah, you just square root X. And by doing that, what does that enable me to cancel? So you're just graphing y equals root X plus 1. And you guys should know this. There's a shift. What's the shift? Yeah, if I plug in 1, I should get 2. Plug in 4, I should get 3. So there's the graph. So for what value of X? And actually, I did lie. I didn't do the graph correctly. I made a slight error. What did I do wrong? Why?
Visible.
Mm-hmm. Can't plug a 1. So still undefined. So if you're asked to find the limit of it, well, I just do what I just did, right? I'm just going to repeat what I did up above. You can do the conjugate, by the way. Actually, do you guys want to do the conjugate, or how do you guys care? Or you want to factor it? What do you guys like? Let's do conjugate. Let's do another way. If you do the conjugate, you multiply top and bottom by root X plus 1. And when you do that, you get X minus 1 still. Root X plus 1. And what does bottom come now? X minus 1, those cancel. And then you can plug 1 in, and you get 2. The graph shows it clearly. And we've done this already on the quiz, right? Something like this. Now, this part's new. No, it's not new. Identify the type of discontinuity X equals 1. Well, f of 1 does not exist, but the limit as x approaches 1 of fx exists. What do we call that when that happens? When the first condition of continuity fails, the second one passes? Yeah. Or removable. So when the function itself does not exist, or say it does, and the limit exists, but the f of 1 doesn't equal the limit as x approaches 1, when the point is not the same place as the limit, it's still the same thing. If the first two pass, but the third one fails, that's still removable or point discontinuity. But you need the limit to exist by. Now, what if the limit did not exist, but they approach finite values? So it's kind of like this. Then we call that jump. Call it jump if that was, if, you would see it on the graph itself. But yeah, so that's part C. Right, correct. So looking at part D now. You're asked to write an extended function. An extended function is the forced continuity. You want to force the continuity. So how would I write it? You can write it two ways. You can write it like this, or you can write it like this.
Would you write after?
X does not equal 1. Yeah. So in order to force the issue of continuity, you want to fill in that hole, right? So what do I mean by that? Fill in the hole. You do it two ways. You could write it either simplified form, or you could write it piecewise. Totally up to you. Now, sometimes I'm going to put a little star here, or asterisk. The simplified form may not be an option, depending on what kind of function you're dealing with. But this is always a guarantee. Because guess what? Just write the darn function originally and tell me what y value you want to fill it in. That's it. That's always a guarantee.
Wait, do you write in function so that you can get like a valid limit or something?
So you can get continuity everywhere in the domain. That's why.
What?
Root x minus 1. Yeah. It's just the original function.
But in some of these discontinuities not have seven functions, so
Oh, sorry, say again?
like if there's an infinite discontinuity, there must still be an extended function.
Um, Good question. If there's continuity. No, it wouldn't be continuous because the left side would be going towards positive negative, or one side. So you wouldn't, yeah, you wouldn't be able to do that. You could put a point at the vertical asymptote just so the domain's all real numbers, but it would not be continuous because the limit wouldn't exist, right?
Yeah.
Because once you have infinite discontinuity, forget about it. It just can't happen. It's only for removable we can do this. So yeah. Um, okay, let's try this again. Let's look at example 2. I won't move the screen so you guys can see this still. So for example 2, analytic determine the limit. Great. Write an extended function. Great. My extended function, I'm just going to get out of the way quickly. Or you could write it like this. And what's going to fill in the hole?
-4.
-4. I mean, when x is -2, of course. Wait. Yeah, I got it. Yeah, we're good. Because x equals -2 is a problem, right? You get 0 on the bottom. But I factor it, I can cross off x plus 2's. So what does this mean? What does that graph look like then? So this helps you understand these better now. What does this graph look like? It's a line, but with a hole. Where's the hole?
-2.
-2 comma -4. There you go. And if you want to make it seem complete, fill in the hole right there. That's it. So that's how you make the extended function. So now you guys are aware of that, which is good. Analytically determine the limit. You guys can do that. I'll do it really fast. The limit as x approaches -2. This junk, I'm gonna start factoring it right away. What happens to x plus 2s? They cancel. So now I can plug in -2. And what do you get? -4. There you go. Because the limit does exist, but f of -2 did not. So if you want to be continuous, you better put a point f of -2 and fill in that gap. And therefore, will the limit equal f of -2? 100% will. We're all good. Okay. Let's keep going. Let's do this again here. Okay, we've kind of seen this already. There's a hole here. So how do you want to take care of that? Piecewise, yeah. Now, this is what I was saying. I can't really simplify this, right? So I'm just going to do this. And I actually should put parentheses x, by the way. I got a little lazy. I should do that. Sine 3x over x. And this is true when x does not equal 0. But when x does equal 0, what do I want? There you go. Done. That's it. It's not that hard. It's really simple. Yep. It's kind of dawned upon me. Do you guys use Albert IO? Okay. I think I might try to add you guys to Albert IO for AP Calculus because I have access to it. And I think you guys might appreciate some of these extra practice problems. So Delta Math is not sophisticated enough. That's the only problem. Yeah, that's the only. I like the interface better. Albert IO could be a little clunky. Okay. Now, let's keep going, guys. Continuous functions. What is a continuous function? A function with no breaks in it. For its entire domain. It's not a super sophisticated definition, but a function with no breaks in it, right? For its entire domain. And by the way, the properties of continuous functions, it's still using common sense. If you add two continuous functions, they're continuous. You multiply two continuous functions, they're continuous. Subtract them, divide them. So it's all just kind of common sense. Like, for example, is sine a continuous function? Yeah. Is cosine a continuous function? So what if I ask you, is sine x plus cos x a continuous function? Yeah, just put in Desmos. There's no reason why there'd be a restriction, right? Or is cube root of x a continuous function? Sure. Is x squared a continuous function? Sure. So if I do x squared plus cube root of x, that's continuous, right? I expect that to happen. Or if I multiply whatever, right? Yeah, if it is sine x times cos x, right? Same thing. Oh, this is an interesting one. What if I did sine x divided by cos x? It's tangent, so it's not continuous for all real numbers, right? So there will be some breaks, obviously, like some vertical asymptotes. So that's why the little caveat, provided GOC does not equal 0, you have to be mindful about that. Okay, ask what I was having as a teacher, I absolutely love exam 4. I love that problem. And I actually can make this more complicated. I'll show you some complicated ones in a moment. I love these problems because it really forces the issue of continuity and it brings back some old algebra skills. So here's the deal. You got a piecewise function. If I do a quick sketch, I kind of know this will happen, right? 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, if I plug in 2, I should get 3, right? Yeah. And it's included. The vertex is at 0, -1, of course. We're going to the left. If I plug in 1, I should get 0. Is that right? So it kind of looks like this, right? Not the best looking graph, but we have that right. Now, this one here is a little funky. Like, for example, I don't know what A is. I have no clue. But you want them to be continuous. So what it means is that you want them to link up at x equals 2. Because can your piecewise function look like this? It could, depending on what A is. I don't know. Or it could look like this. Sure. Well, what do I really want? I want something like this. I want them to link up. Yeah, I want them to meet up at 3. 100%. I do. So let me show you the quick and dirty way, or quick and easy. Okay, quick and easy. Just do this. What am I doing here? I'm just plugging 2 in, right? Oh yeah, duh. Thanks. So 4 minus 1. What does that equal? 7. Okay. On the multiple choice exam, which I might throw in some multiple choice on this test. I might. But there won't be like SAT style. There'll be more College Board, AP Calculus. I'll give you some examples. Hopefully by Wednesday I'll get a chance to do that. That's a quick and easy way. So, or on the AP, like a year from now, when you guys are studying for the AP exam for AP Calculus, just do that because they will probably ask this question. I'm almost certain this question will be asked. It's asked almost every year. Yeah, just do that. Does that make sense? How they link it? Yeah, because if I put 7, even though it's way up here, 5, 6, 7. So I know it's way up here, but if you think about it, now if I put in 1, I get 6. But see, they link up over here, right? So that guarantees that there's a link. So yeah, that's a quick and easy way. However, there is a formality. And now for your response on the AP exam, and I do need to start training to think this way, you kind of have to show kind of all the steps. I mean, some of you guys had APs last year, and not the sophomores, obviously, but or maybe you did, I don't know. But those juniors, you guys had APs last year, and there's a rubric and there's like a guideline they have to follow. We have to adhere to that. So what's a formality? You have to use the definition of continuity. So what I want you to do is this. The first condition. Does f of 2 exist?
Yeah, you just do quick and easy with some
Limits?
multiple choice.
Was that?
With multiple choice.
Yeah, but I'm saying if it's free response. Yeah. Does f of 2 exist? What was f of 2? So check. Okay. This is the big one. Does the limit of as x approaches fx exist? We're going to say yes. And we're going to force the issue. How am I going to force the issue? The left-hand limit must equal what?
Mhm.
So the limit as x approaches 2 from the left has to equal the limit as x approaches 2 from the right. So you have to show that to me. I need to see that. I'm running out of space, so I'm going to go out to the left here. So when I do that, the limit as x approaches 2 from the left, I'm going to say 2 squared. So now I'm getting back to the quick and easy way. But I had to first write that limit beforehand, right? And then, of course, negative 2 squared plus a. So 3 equals negative 4 plus a. What does a equal? So let's say check. And applying for your third condition, so f2 equal the limit. So 3 equals 3. Yes. So you have to do that. That's what I'm looking for the formal definition of derivative. Sorry. That's, wow, that's like a few weeks from now. Formal definition of derivative. Sorry. Formal definition of continuity. We're not at derivatives yet. My apologies. All right. So that's all I want to talk about today. I think that was plenty of stuff to share with you guys today. Do you guys want more math today? You're good? All right. Okay. I'll give you guys more math. So that's what's happening. So if we look at the homework, so the homework, I'm gonna have to make an update or just kind of tell you what to kind of guide you. We're still not going to do the 1, 2, and 3 yet. That's for after Wednesday. Um, and these are good to do. So I might assign some of these problems here for as x approaching infinity, but definitely the extended functions for sure here, like 25, 28, 29. I don't care for 33. I'm gonna leave that alone. I like 48. I like 50. Definitely want to ask those questions. Definitely want to ask 1, A and B, 2, A and B, 3, um, yeah, A, B, C, there's a D twice, so the top row there. Um, and probably 6 as well. And I think that will be good for, and actually, if you guys could handle these problems also, like drawing a graph with all those conditions, I think you guys can handle that. So I'll probably throw that in there as well. Um, more on continuity. Maybe I'll sign those, or I could hold off on that. It's a little too much. So I'm gonna update Schoology right now. But if you guys do want to get a head start, probably start with page 9. I'll write on the board actually what I want you guys to do. Ooh, there's some good ones here too. Well, because these are circled, yeah, that's fine. Actually, I think they're copied from this. Yeah, I think they're copied. So let's do I'll write on the board. Page 8, 22, 25, 26,
Oh, really?
and 42. And 43. And we're not doing a quiz this week, so just um, I haven't graded them yet. Page 9. Yeah, 25, 20, 29.
Wait, it was the.
Yeah. 48, 50.
Oh.
And page 10.
Yeah. But like, a lot of people do that like. I'm really excited. I was still just like simple time.
Yeah, no, that's fine. Yeah, either way.
Yeah. Wait, yeah, you just like. Oh, you like what they didn't have, they need these. I don't know if you did, but like, it's like where yes and no on inside. Yes, and then
I think it's fine. I won't do anything on the next page. We're good.
Yeah. Oh. Oh, yeah, I don't have hope. That's like my pink reasons. Oh, yeah, I don't have it. That thing. It's like it's one. It's one. That's the pink one. I just like massage it. Yeah. Okay, I'm probably supposed to. You know, like those erasers as a little side that was like what's the whole. I know what you're talking about. It's like in half, right? Like 50s and yeah. I'm not the that's not there was spent. It was a four. It's just like for at least it's like what will be for what? For like heavy meals. Oh, they do have to they do my side of the